Hello everybody. So the very last thing we have to understand in this course is how to find area and length when we have curves in polar coordinates. So let's get started. And what kind of regions are we finding the area of? So it's going to be the region bounded by some curve and the lines theta equals A, theta equals B. So here is, let's see what this is on a picture. So here we have some curve R equals f of theta. And here f is supposed to be a positive continuous function, so there is no crazy jumps or anything like that. So f is positive, here is r equals f of theta. And then we have the lines theta equals A, theta equals B. So remember we said that theta equals A is the line through the origin that makes an angle A with the positive x-axis, and theta equals B is the line that makes angle B. Okay, so we have some kind of region like this. It's bounded by the lines and the curve, and we want to find its area. Okay, how could we do that? Well, one thing we could do, as we usually do in calculus, is it's a complicated shape. We don't have a formula for this complicated shape, but we could split it up into lots of small pieces. Say we split up this curve into lots of little bits, and then each of those little bits we could approximate pretty well by a semicircle. Okay, the whole curve doesn't look like a semicircle, but we could approximate each part by a sector of a semicircle, maybe a very, very thin sector of a semicircle. And we know how to find the area of a sector of a semicircle, right? If the angle is theta, it would be a half r squared theta. Okay, we find these areas, we add them up, and we put it all together. So that's the idea. Okay, so if you do that, then you will get sums, and then you will let the individual pieces get smaller and smaller. You'll take a limit. The sums will become an integral. Okay, it will give us this formula for the area of a sector of for the area of this region R. So it's the integral of a half r squared d theta, or since r is f of theta, it's the integral of a half f of theta squared d theta. Okay, so pretty straightforward, but do keep in mind that the sectors that we're finding areas of look quite different to what we had before. So in the past, we've had a curve y in terms of x or x in terms of y, and we found the area bounded by the curve in the x-axis or the curve in the y-axis, and pretty similar when we were doing parametric curves. Here, it's not an area bounded by a curve on the axis, it's the area bounded by the curve and these half lines theta equals A, theta equals B. So we want to keep that in mind when we do these area calculations. Anyway, so here is an example. So we have the curve R equals cosine of 2 theta. So it has this strange shape. And we want to find the area of one loop of this curve. So we have to figure out what are our theta values. And it turns out if you analyze this curve a little bit, R equals cosine of 2 theta. Okay, it goes through the origin several times. So if we want to find one of these loops, we have to find two close by values or two subsequent values where it goes through the origin, right? If I start here, over here when theta equals 1, I'm going to end up at the origin, and then, okay, what was the theta value back on the other side? And it turns out, okay, cosine of 2 theta equals 0. 2 theta has to be pi over 2, which is going to give us pi over 4, or negative pi over 2, which is going to give us negative pi over 4. And then there will be lots of other solutions, of course, which are the other three loops. So at least one solution to give us one loop, the rightmost loop, would be theta equals pi over 4, theta equals minus pi over 4. It's when we pass through the origin. Okay, so those are going to be our limits. We integrate the theta values, so negative pi over 4 to plus pi over 4, a half r squared d theta. Okay, we know that r is cosine 2 theta. So we get a half cosine squared 2 theta, everything all in terms of theta. And now once we set up our integral, we can just forget completely where it came from. Okay, we have to integrate this. We have cosine squared of something, cosine squared 2 theta. So we want to convert to higher angles but lower powers if we use our double angle identity. So doing that, cosine squared 2 theta is a half 1 plus cosine of 4 theta. When we go down in powers, we double the angles. So with the half we already had, we're going to get a quarter 1 plus cosine of 4 theta. And then we integrate, plug in pi over 4, plug in negative pi over 4, and subtract. So the 1 over 4 times 1 is going to give us 1 over 4. We integrate, we get theta over 4, and then we plug in the pi over 4, the minus pi over 4, we get pi divided by 8. And then a quarter cosine 4 theta is going to become a quarter, or 1 over 16 sine 4 theta. And then we plug in pi over 4, we're going to get sine of pi, which is 0, sine of negative pi, which is 0, so the other pieces fall out. So we're left with pi over 8 for the area of the loop. Okay, one thing that we saw back with y in terms of x or x in terms of y was finding the area between two curves. And typically, if we had y in terms of x, we would do the top curve minus the bottom curve. Here we can have a similar thing where there are quite complicated areas bounded by multiple curves. And in that case, rather than doing the top curve minus the bottom curve, we want to do the outermost curve minus the innermost curve. So now kind of inner curves are close to the origin, we imagine. Outer curves are the ones that are far away from the origin. So if we want to find the areas, we want to do the outermost curve minus the innermost curve. And I'm not going to do an example like that in the video. I'll save that for class so that I don't have to draw too much right here. But let me mention that when we're doing this, we're finding the area of the outermost curve minus the area of the innermost curve. The theta values for our limits are going to be the intersection points, just like when we had curves y in terms of x or x in terms of y. So we have to find the intersection points of the curve. But unfortunately, in polar coordinates, if we have two curves, so r equals f of theta, r equals g of theta, solving where f equals g, so solving where they're equal, does not always give us the points of intersection. Unlike back when we have curves y in terms of x and we solved for when the y equations are the same. So why does this happen? The problem is that there are multiple ways to represent points, and in particular, there are multiple ways to represent the origin. So it might be that one curve goes through the origin at one value of theta, and another curve goes through the origin at a different value of theta. Or similarly with other points, maybe there's a negative r, maybe there's a positive r, or maybe theta is between 0 2 pi for one and between 2 pi and 4 pi for another. So the problem comes from uniqueness, non-uniqueness of polar coordinates. Okay, so normally it will give you quite a lot of intersection points, but if you want to check that you've got all the intersection points, the best thing you can do is draw them. Okay, but here is an example. So we have two polar curves, r equals 3 sine theta, r equals 1 plus sine theta. So these will be two polar curves, and they both pass through the origin several times. For instance, 3 sine theta will pass through the origin when r equals 0. So that would be when theta equals 0 or pi or 2 pi or any multiple of pi. On the other hand, 1 plus sine theta is 0 when sine theta is negative 1. So that would be 3 pi over 2, and then adding on 2 pi multiples to give us the rest of the values. So they both pass through the origin, and they're still going to intersect at the origin because they're passing through the same point. But we're not going to be able to solve 3 sine theta equals 1 plus sine theta and get all these theta values. It's not going to work out that well. Okay, so one thing we can always do is to graph the curves and make sure we got all the solutions. So if you have a rough idea of the graph, then you can check how many times you think they intersect, and then you can check you got the right theta values. Okay, last thing we have to understand is arc length. So if we want to find the length of a curve, okay, now we don't have to worry about strange regions. The length is just the ordinary length. So you could convert to from polar coordinates to parametric coordinates by using x equals r cosine theta, y equals r sine theta. Then you could use the length formula we had for parametric coordinates and simplify as much as you can. And it would turn out you get the formula a little bit like this, or exactly like this. So the length is the integral from a to b, so theta equals a up to theta equals b, of the square root of r squared plus d d theta squared d theta. So, and the usual the usual warnings occur when we have square roots, right? We want to be careful with the square root. The square root of a sum is not the sum of the square roots, but anyway, this is just like we've seen. So for instance, let's find the length of the curve r equals theta squared. So where theta is between 0 and 2 pi. So all we have to do is plug in, see what we get, and then try to do the integral. So we have r is theta squared. So r squared is going to be theta to the 4. So we have our theta to the 4. And then d theta is going to be 2 theta. We square it, we get 4 theta squared. So we have to integrate the square root of theta squared plus 4 theta squared. And we see straight away that both terms have a theta squared in them. So we can pull out that theta squared. And since we're pulling it out of a square root, the square root of theta squared, we get a theta. So we just have to integrate theta times the square root of theta squared plus 4. Okay, and now you could do a u sub, for instance, of theta squared plus u equals theta squared plus 4 because there is a constant multiple of the outside, or there is a constant multiple of the derivative on the outside. So it's set up as a simple substitution. Okay, all these simple substitutions are basically the reverse of the chain rule. So you can notice that an antiderivative of this is a third theta squared plus 4 to the power 3 over 2. For instance, if we were to differentiate this, differentiate it, so the outside is a third u to the 3 over 2, the inside is theta squared plus 4. So if we differentiate the outside, which was a third u to the 3 over 2, the 3's are going to cancel, we get a half u to the 1/2, and then we multiply by the derivative of the inside, which is 2 theta, so the halves are going to cancel. We're just left with theta square root of theta squared plus 4. Okay, and then we have to plug in 0 and 2 pi, or if you did a u sub, you would have to transform the limits and then plug in. So we plug in and subtract, we get the answer. But however you like to do that, u sub is perfectly fine. Okay, so in this video, we saw how to find areas bounded by curves in polar coordinates, and then we want to be a little bit careful. Theta equals a, theta equals b are half lines, so it's not like when we had y in terms of x or x in terms of y. And then we found a formula for the length of a curve, which just comes from converting to parametrics, and it's pretty simple to apply. We just substitute in and integrate. Okay, thanks everyone. Thanks for watching these videos, and I hope to see you in class soon.